This is problem 111 of Neetcode 150 unique path. So we're going to be given basically m by n grid, and we are allowed to move either up. No, sorry, we have to move down or right. So we cannot move up. We cannot move to the left. We are being told that we need to provide the number of unique paths that we can take to reach the bottom right corner. All right, so let's jump into the solution right away. So the problem itself is not super hard once you figure this out. You can actually solve this in a linear time if you're using some math equations, but I mean, I'm not gonna assume that you have, and I don't have a background in math plus CS, so let's just stick with the CS side and do some dynamic programming to solve this. But if you're curious, you can still see the math solution on Neetcode's websites. So let's say that we have let's just draw this quickly. So we have 3 rows and couple columns. 1, 2, 3, 4, 5, 6, and 7. All right, so the trophy is here. So let me just put a E for the N. Right, and the start is here. So when we start from an edge, whether it is the bottom or the vertical right, so along this path and this path, well, how many solutions do we have? How many unique paths do we have? If we can only move down and right, well, we won't, right? Because we can't go down, we can't go up, we can only go to the right up to the endpoints. And same thing here, we can only go down up to the endpoints. So that's good, but now what if we want to start here? Like, how many paths do we have? Well, if we go to the right, we're gonna be on a case that has one possible path to the end. And if we go down, we're gonna go to a path that only has one possible path till the end. So what we can conclude from this is that at this particular cases, we basically have two solutions. And now what we do if we are starting from this case? Well, if we go to the right, we know that we have two possible paths, two unique paths to reach the endpoint. And if we go down, we have one unique path to reach the endpoint. So basically you can have 2 plus 1, so 3 paths. All right, I will do this one more time, but I think that at some point you're going to catch the pattern here. So if I am here, I can go to the right. And if I go to the right, I have 3 unique paths from this very cell. But if I go down, I have 1 unique path, meaning that at this particular place, I have a grand total of 4 different options. Cool. So if we keep going, I think that it will make sense for you to acknowledge that we have here 5, 6, and then 7 unique paths from these cells. Actually, my S looks like a 5, so I will just erase this and maybe take another color. So let's pick pink. All right, so let's say that this is a start. And I'll put ST just to make it clear. All right, so we could take a look at this case. I think that it will make sense for pretty much everyone that the same logic applies here. So if we go down, we're gonna have a cells with 2 unique paths up to the endpoint, and if we go to the right, we have only 1 unique path to reach the end. So I will have here a number 3, and well, obviously at this case that has basically 2 paths, so right and down, and to the right we have 3 solutions, and to the bottom we have another 3 solutions. All right, so we're gonna have basically 6 solutions at all. I won't let you guess the rest, right? So this is 10. Now we're gonna have 15, and we're gonna have 21 here. So at this very at this cells, we're gonna have basically 28 different paths we can take. So what is the logic here? Actually, we can do this with a space complexity of big O of n, where n is basically the len of basically the of a single row. Here, our single row is actually 6 of len. So this is good. What we're going to be willing to do is that we're going to keep basically like a value 1 for each cell. And we're just going to keep track of their indexes along a particular row, not necessarily the row, because it is not super important. And what we're going to do is that we're going to start from this very cell. So if this is of length 3, we're going to be willing to reach the index 1 here for like the row, the index 1. So you can see that we're going to have basically something that looks like this. So m minus 2. And same thing also for the index within a row. So if a row, like right now it's of length 7, but we want to reach the index 0, 1, 0, 1, 2, 3, 4, and 5. So we're also we're gonna be willing to start at n minus 2 index. And what we're gonna do is that we're just gonna basically set that particular value here to be plus equal the value to the right every time. So now it's gonna be equal to 2. And when we go there, because we're gonna basically loop through all of these in this order. So we're gonna go there. Now we're gonna go here. All right. So, oh, anyway, so we can tell that from the second row what we're gonna have at every single position in our linear array of solutions. Well, we're initially gonna have 3, and now we're gonna have 1 plus 3, so we're gonna have 4, and then we're gonna have 5, then we're gonna have 6, and then we're gonna have 7. And then when we're gonna do our second while loop for the very first row, well, we're gonna still do the same thing. So we'll do 2 plus 1. So here I will have a 3, and then I will do that value itself plus the previous one. So it's gonna be 3 plus 3. So I will have 6, and then again I will do 4 plus 6. So I'll be at 10. And see that by doing this, we're actually going to end up having 28 here at the index 0 in our DP index or DP array. So let's put this in code now. All right, so first thing that we want to do is that I'm just going to create basically DP, and in DP, I will store an array. Well, it will be an array of ones, and I want to make sure that I have basically n times 1, n is the length of a single row. And now I will go basically for all the row, so for r in the range of, and now I will say m minus 2. And I want to do this starting from the bottom right index, right? Well, as far to the right and to the bottom as we are interested in. So I will do basically a reverse for loop. So I will stop at the index 0. This is why I have my minus 1, because my minus 1 is my bounding index. So I will stop at index 0. And I will also do this in a reverse order, which is why I'm adding minus 1 as the third value. And then I will be willing to go to every single column inside this row. So I will say for C in the range of n minus 2. And once again, I want to go up to the index 0. So I'm going to include a bounding index of minus 1. And I want to do this in a reverse order. So I will use a minus 1 on the third value as well. And what I want to do basically is that I want to set that value of the dp at that at the index of the column that we're at, I want to make sure that I increment this. I increment to this value the basically the column that is to the right. So it's going to be c plus one. I hope this makes sense. That's what we discussed in the example. And then we can simply return the dp at the index 0, and this is going to give us the right answers, right? So in terms of times and space complexity, we're going to basically do a while loop. We're just going to have two for loops. So we know that we're going to have basically two values multiplied. And the two values are basically the length of the column and the length of the rows, meaning that our time complexity is going to have m by n. And our space complexity is basically the length of a single row. So it's going to have a space complexity of big O of n. With that being said, I hope you enjoyed the video. I hope you learned, and I hope to see you in the next one.